Hello, everyone. Welcome to the second presentation on flooding that's being given as part of the METEOR project. My name is Chris Sampson. I'm a flood scientist, and I led much of the flood modeling that has been done as part of this project. The first presentation that we gave introduced flood modeling and some of the core concepts. This presentation focuses on the national scale models that were produced for this project and how the data produced by those models might be appropriately used. So a quick overview of the presentation. We're going to talk about some of the key national scale data sets that went into the model. We're then going to talk about the methods that we used to employ those data, and we're going to look at how the data might be applied. So to start with, I'd like to make a couple of key observations about national scale models. The first is that these models require a consistent methodology. This is because many end users of national scale models want to be able to compare between locations, and that's very difficult to do if you produce different models using different types of data in different locations. The second is that in the territories that the METEOR project operates in, local observational data was usually not available. This means that the models had to be able to operate using open access, nationally available data. And in many cases, that meant globally available data sets. And this does have implications for the accuracy and precision of the models because they are limited by the quality of those data. Now, perhaps the most fundamental data set to a flood model is the terrain data. It's absolutely critical. Because of the limited availability of local scale terrain data sets, we had to use remotely sensed global data. Now, this kind of data is collected by satellite, but it's not collected by satellite specifically for the purposes of flood modeling. And this means that it requires a fairly comprehensive amount of processing in order to make it usable within a flood model. The data that we used for the METEOR project was the MERIT digital elevation model. This is a global terrain data set that we helped to develop with colleagues in Japan that has a resolution of 3 arcseconds, which is approximately 90 meters, and is based on the United States NASA SRTM, Shuttle Radar Topography Mission data set. But it's had an awful lot of processing done to it in order to remove many of the biases and noise that exist within SRTM. And the result of all of this work is that the MERIT terrain dataset has significantly improved elevation accuracy in flat regions. And of course, when we're worried about flooding, it is the flatter parts of the landscape that are at risk. And therefore, these improvements are felt very keenly in this application. This slide here shows you quite how significant these improvements can be. So this is the Mekong Delta that we're looking at here. And on the left-hand side, you can see the raw, uncorrected SRTM data. So this is the data as it were collected by the shuttle itself. And on the right, you can see the processed MERIT terrain data. And you can see very clearly that a load of striping error that's present in the raw data has been removed. And if you run a flood model on a terrain data set that has stripes, like you can see in the left-hand panel there, you get some very strange results. So this indicates the importance of performing this sort of analysis on the data that goes into a model. Now, the next key data set that goes into a flood model is the hydrography data set. Now, hydrography just refers to the river network and associated characteristics such as river width, river upstream area. Now, the basic hydrography network is derived from the elevation model, but it can also be conditioned with other open source data where available. The hydrography dataset that we use in this project is MERIT Hydro. So it is related to the elevation model that we just talked about, but it was then fused with a number of open source data sets, including OpenStreetMap data and Landsat imagery, to better constrain the location of rivers throughout the landscape. And MERIT Hydro today represents the best open source global hydrography dataset that is available, and it's used very widely by the scientific community. Now, when you are building flood models at national scales, it's very important to automate the procedure. Traditional small-scale flood models were constructed manually. That means that the input data was collected manually and surveyed manually. It was then entered into the computer software manually. The model was calibrated manually, executed manually, and the resulting output data was processed manually. Now, whilst that's a perfectly reasonable approach for a local reach scale engineering project, it is, of course, not feasible to do at the national scale. And therefore, national models require an automated framework that brings in all of the various input data and model components and constructs and executes the models on its own. Now, the details of our framework are laid out in the accompanying scientific literature, but a schematic for the model is on the slide here. You can see that conceptually it's quite simple. It takes the inputs in terms of terrain data and river topography. It takes also inputs in terms of river flows, and it uses these to build the input conditions for the model. The model is then executed and the flood layers are produced. So with that said, I want to give a very quick run through of some of the key methods that model builder uses. I can't go into the full detail on this presentation, but hopefully this will give a sense of what the model is doing. So in terms of the terrain data, the global data set is processed into 1-degree tiles that then have a buffer added to each side to allow the resulting simulation output files to be blended back together to create a seamless national data layer. A traditional reach scale model would use a nearby river gauge to estimate extreme flows for that area. Now, unfortunately, for most of the terrain that we were simulating as part of this project, there were no local river gauges. That means that we had to use a regionalized method in order to estimate appropriate extreme flows to place into the model. And this method is known as the regional flood frequency analysis method, and it uses river discharge data directly from thousands of river gauges around the world. And what it does is that it links the flow behavior of each of these gauges to predictor variables such as climate zone, area, rainfall, and slope. It then performs a clustering analysis on these gauges and their predictor variables in order to generate a model that can then be deployed anywhere on the planet. Validation work performed on this method has shown that it has similar levels of skill at predicting extreme flows to ungauged hydrological models. So this suggests that the approach is entirely appropriate for estimating extreme flows for areas that we don't have observations. Now, for the rainfall component of the model, we use intensity, duration, frequency, or IDF curves to define design rainfall events. And we simulated the 1 hour, the 6 hour, and the 24-hour rainfall events for each return period. Local data was used to characterize these IDF curves where available, and where it wasn't available, a regionalized method similar to the flow discharge method was used to estimate appropriate rainfall intensity values for each event duration. Now, as we already mentioned, MERIT Hydro was used to define the location of the rivers, and a global river width database that used Landsat imagery was used to estimate the widths of rivers. However, the one thing that cannot be estimated from remote sensing is the depth of rivers. And that's the one other component that is essential for the flood model, because in order to know how big a river is, you need to know approximately how wide it is and approximately how deep it is to get an idea of how much volume it can convey before it starts to go out of bank and cause flooding. Because you can't observe this information, it has to be modeled. And we use a one-dimensional channel solver in order to do this. Now, conceptually, this model is quite simple. What it does is it takes the 1 in 2 year flow from the flood frequency analysis and assumes this to be bank full. The solver then calculates the appropriate channel depth, given the width and given the slopes from the elevation model, to yield a water surface that's level with the elevation model at that point. By assuming that the elevation of the terrain model at a point is equal to the bank height of the river, we have a way of calibrating the river conveyance within the model to carry that 2-year flow before it starts to flood. And the 1 in 2 year flow is approximately the bank full return period of a river in its natural state in most locations. Now, the automated model builder then has to decompose the river network into segments or reaches and generate a hydrograph or an inflow boundary condition for each of these reaches for the model to then simulate. The regionalized flood frequency analysis gives us the discharge for each boundary condition, and we use an estimate of time to peak based on the distance to the furthest point in the catchment in order to estimate how long a hydrograph should last. The rainfall events for each model domain are defined using the IDF curves that we just mentioned. Now that the framework has generated all of the boundary conditions, it has to execute. It does this using a full 2D hydrodynamic model based on the simplified inertial variant of the shallow water equations. Now, I talked about these in a little bit more detail in the previous presentation, but the important thing to note about them is that the physics is simplified as far as possible in order to maximize the speed of the simulation and minimize the amount of computational power that it requires, while still preserving enough precision and accuracy to give a good result. The other thing that's worth noting about the implementation of the hydraulic model in these national scale models is that for the river system, it uses a subgrid method. And what that method allows is for the width of the rivers to be decoupled from the grid. Now, when you use the data, you will know that the grid scale is about 90 meters. This method allows us to simulate rivers that are much smaller than that, because actually a 90-meter wide river is really quite a large river, and it's necessary to simulate rivers that are far smaller than that because they can actually contribute an awful lot of the flood risk. So this subgrid method allows us to do that. The final stage of the process after the simulations have run is to pull together all of the different reach simulations within each tile and merge them, and then merge each tile to create a national scale layer for each return period. Now, this might sound trivial, but there will in fact be many thousands of simulations for each layer that are performed. And so again, it's very important that this process is automated and efficient. The final step is to take these output data and transform them into a standard GIS format, for example, GeoTIFFs. And on the screen here is just an example of what some of the flood output might look like. Now, given the context in which these models have been constructed and the data limitations that they are faced with, it's very important to consider where they can and cannot be suitably applied. Now, on the table here, you can see potential applications for this data for a number of different stakeholder types, be it the public, be it local government, be it insurance or commercial. Now, you will see from this table that the information produced by these flood models is very useful for things like flood and awareness programs, flood hazard communication, and identifying areas and regions that are likely to be at risk. However, it has limitations when you start to reduce the scale at which you're trying to apply the information, and it's clearly not appropriate to apply this information for individual property level decisions. Another way to frame this is to consider application scale. If we start at the national scale, the data is clearly appropriate and suitable to generate a national scale hazard assessment. If you're looking to determine which catchments are risky or the relative level of risk between catchments, the data should also be able to provide a good assessment of this in all but the very smallest of catchments. Once we start to look at individual settlements, the picture becomes a bit more mixed. For larger settlements, such as towns and cities, the data should be fine to assess whether or not that town or city is exposed to significant flood hazard. However, as we move to smaller settlements and small villages, we may be reaching the point at which the scale is becoming too small for the model to have adequate skill. And if we get down to the individual building level, unfortunately, the data is not appropriate to assess flood hazard for individual buildings. And that is fundamentally because the underlying global terrain and hydrography data sets are not precise enough for this kind of application. If we move on to infrastructure, a similar logic applies. The data can be used to assist in planning decisions, and it can be used to determine individual locations and individual pieces of infrastructure that might require a more detailed engineering investigation. However, the data cannot be used to make design decisions, and it cannot be used to define the specifications of individual pieces of infrastructure. So therefore, there is a general picture that the data can be used to infer areas and regions, towns and settlements that may be at greater risk of hazard and require more detailed local information, but it can't be used to make detailed design or engineering decisions at the individual building level. The final slide here is a list of key academic references for more detail on the methods and the data that are used in this model. These papers are available at the DOI links provided for each. Thank you.